All right, so far I haven't got any emailed questions. Well, actually I did get one, which I'll talk about to begin with, but actually let me back this up just a little bit. There we go. But if you do have questions, ask them in the chat. The one I got asked this morning was about these conversions between concentrations. So I want to preface this by saying these problems are a lot harder than they're going to be on the exam. The most important thing you can take away from this, molarity and molality are going to be roughly the same when you convert between the two. So when you go between molarity and molality, you should be getting roughly the same answer. And they're going to be about 100 to 1,000 times bigger than the weight fraction, or somebody asked yesterday, WWGG. WW I think is technically for, come on, get back in focus there. WW is technically for English units. GG is for metric units. That said, we're in chemistry course, we only work with metric, but if you do see WW, it refers to the same thing. Now, to solve these types of problems, we start the same way. We've actually got 3 parts. So part 1 is what we're given. Part 2 is converting. And part 3 is just a definition. So we've got molarity, big M, molality, little m, and our weight fraction. So if we're given molarity, we're going to assume 1 liter of solution. Now, do we have 1 liter solution? No, but we're going to assume it. And the reason we're going to assume it is that concentration does not depend on how much we have. It's an intrinsic value, so it's like density. The density of something doesn't increase as you get more of it. The mass of it does, but the volume increases at that same rate, so the density stays constant. For molality, we're going to assume 1 kilogram of solvent. And for weight, we're going to assume 1 gram of solution. Now, reason we're making this assumption about 1 is that it makes life really easy. So if we have a molarity and we have 1 liter solution, that'll tell us how many moles we have, because by definition, molarity equals moles over volume. Molality equals moles over the kilograms of solvent. And your weight fraction is grams of solute per grams of solution. So based on this assumption, we're going to get 2 numbers. We're going to get how much we assumed, and we're going to get how much solute is in our material based on that assumption. From there, we've got 3 formulas. And the 3 formulas are that the density of the solution is the mass of the solution over the volume of the solution. We've got the grams of solution also equals the grams of solute plus the grams of solvent. And we've got that grams of solute is the moles of solute times the molecular weight, MW, of the solute. So based on this one assumption, what you're going to do is you want to see where you're going to and where you want to go to. So let's say you're given molarity and you want to go to molality. So tilt the picture, tilt the light a little bit to help you see it better. So if we want to know molality, we need to know how many moles of solute we have and how many grams of solvent we have. So if we assume we have 1 liter of solution, that'll tell us how many moles of solute we have based on that. So we've automatically got the moles of solute. And we can take our 1 liter solution, our density of solution, to get our grams of solution, take our grams of solution to get our grams of solvent, and then we're going to convert our grams of solvent to kilograms and basically recalculate it. If we're given molality, and we're asked to go to the weight fraction here, well, we're going to assume we have 1 kilogram of solvent. That'll give us however many moles we have in that. We can take our moles of solute and figure out our grams of solute using this formula. And we know how many kilograms of solvent we have. We know how many grams of solute we have. So we can figure out our grams of solution. So all you're doing with these conversion problems is saying, okay, for easy math, let's just assume I have 1 of whatever is the denominator. So if I've got molarity, I'm going to assume I have 1 liter solution. If I have molality, I'm going to assume I have 1 kilogram of solvent. If I've got mass per mass, I'm going to assume I have 1 gram of solution. I've got these three relationships, and I'm going to look at where I want to go and figure out what variables I need. So if I want to go to molarity, I need to know my moles of solute and my volume of solution. If I want to know molality, I need to know how many moles of solute I have and how many grams of solution I have. And if I want to go to weight fraction, I need to have my grams of solute and my grams of solution. So I'm going to use the information I had from my assumption and the conclusion I can draw from my assumption, manipulate these formulas, get the variables I need, and then literally just take those numbers and take the ratio and calculate it. It is a lot of work. But that said, the exam, this is a multiple choice question. So that should be the big hint for you. It is a multiple choice question, and you're given some starting concentration said, oh, convert this to another unit. You know what the orders of magnitude should be like between the two. Molarity and molality do not equal each other, but they are close in value to each other. And you know that the weight fraction is going to be about 100 or 1,000 times smaller. So use that to inform your answer. You should do the calculation, but you can check to see if your calculation is right or makes sense by using those orders of magnitude. All right, so that's all I have. Again, these are live streams are not lectures. There is no set format. Basically, I'm addressing any common questions I see in discussion boards and any questions I'm seeing in homework or any questions people ask in advance. But as far as the rest of this live stream, I see there's 3 people watching. If you've got questions, post them in the chat and I'll respond to the questions, but there is no lecture here. Online, there are videos. Those videos will walk you through all the course material. It's constantly an evolving thing, but basically go through that, and if you have any gaps in understanding based on the notes, based on the homework, based on the book, any of that, this is your chance to answer it. These are just office hours, though. You've never had an instructor who's given a lecture during office hours, or at least scheduled one. Otherwise, I will be checking things on the interweb. My left shoulder is still kind of beat up, so I can't really play the banjo today. Oh, speaking of beat up, yeah, here's an ice pack. All right, there we go. what's the problem? Concentration of ions in seawater is approximately the same as solution containing 4.8 grams of sodium chloride dissolved in 125 grams of water. Use this data and a predicted value for the Van Hoff factor to determine the freezing point temperature of the solution. Assume ideal behavior. So formula for this, let's see, is it going for freezing point temperature? Determine the freezing point temperature. So what you use, the delta T equals Kf times I times N. And they're going to have this additional stipulation here that T for freezing point is T minus the delta T for freezing. For boiling, it's T plus the delta T. And so I generally don't focus on what's the actual value of the temperature because it's kind of just an additional superfluous step. This is very much an engineering formula. If you ever go look at the derivation of it, it's literally they just kind of measured it. So once we get this delta T, we're going to take the boiling point of water, which is 100 degrees, and we're going to subtract off whatever the delta T is. So to do this, I need the Kf. This is going to be in a table. The I here for sodium chloride is 1.9. This is also a tabulated value. And then for the molality, let's see here, we got 4.2 grams of NaCl, 1 mole for every 5, that would be 58.5 grams. And to get it to molality, we need to divide by 0.125 grams of H2O. So tell you what, let me bring it up on my computer, and I'll tell you what answer I get. So in terms of my molality, I'm getting 0.574359. You may get slight differentiations of this. I only carry 1 decimal point to use this one to memorize. And then I need to bring up the Kf value. Kf of water is 1.86. So 1.86 times 1.9 times 0.574359. This will give a delta T of 2.029785, trailing off towards infinity. So the new temperature here for the freezing point is T minus the delta T. So the temperature for the freezing point is 0, so you should get negative 2.0. And based on that 4.2 grams, I'd say it's a negative 2 degree shift. So what did the textbook get? So the textbook, we can always reverse engineer their answer and see what they got, or see how they figured it out. So the ions actually come from. So that's what the Van Hoff factor is. So the 1.9 here represents the number of ions that are formed when sodium chloride So the textbook used the grams and went all the way to ions. So can you give me the Van Hoff factor it has in table 11.3? Because this 1.9 reflects the ions. That's why we have it. And the reason why it isn't 2 is that sodium chloride actually, because sodium and chlorine both have charges, they actually absorb some of the H plus and they occupy the H plus and the OH minus in the water. So if they're trying to say that this is 2, I mean, it's going to slightly affect your answer. But again, what was the Van Hoff factor they gave you in 11.3? So the 1.9 is the ion. So I don't understand what the textbook is doing if they're claiming that they convert it to moles of ions, because that's what the 1.9 is. So my guess is the textbook's wrong, which, I mean, it happens. So do they get like -4 for their answer or something like thereabouts to -4? Because again, the reason why we had the Van Hoff is reflect these ions. It's not, we shouldn't be multiplying, we shouldn't be converting to ions. If we're doing that, then we don't need a Van Hoff factor. And even then, the Van Hoff factor is going to be more accurate. So the -2.1 I would agree with. They probably rounded their answer along the way, which is why I got -2 and they got -2.1. But as far as the 4 would go, you keep it in just terms of the molality of the sodium chloride. You don't break it into the ions. That's what the I is for. So I'm guessing you multiplied by 2. So that's why your answer is twice as much. But again, yeah, the Van Hoff factor here, that's how you convert to number of ions. You don't do it directly because sodium chloride doesn't really exist as Na plus and Cl minus in water. It actually exists as Na plus with a bunch of OH groups hanging off of it. And the Cl minus is being next to the hydrogens. So even though theoretically it forms 2 ions, it actually absorbs them -2. So why doesn't the Van Hoff factor come up in Chem 1? Van Hoff factor is an engineering thing. So this is kind of the issue with the material we're covering right now, is that it's not really chemistry so much as it is engineering. So this delta T equals KIM. This is, yeah, you're welcome. This is kind of what engineers develop. But if you ever look up for a proof for this formula, it doesn't exist because no one's actually gone out and proven it. And the thing is that if you take something like sodium chloride, lithium chloride, potassium chloride, rubidium chloride, all these things should split into 2 ions. And if you measure the freezing point changes and the boiling point changes off of just that series of salts, all column 1 metals, just changing the metal, not the chlorine, They all give you slightly different values. So that's where the Van Hoff factor came in, is to say, well, it's a correction factor. It's a fudge factor that accounts for the fact that they don't necessarily split directly into two ions. So we keep it out of Chem 1 because it's not science, it's engineering. It's a fudge factor that makes it work, but there is no theoretical basis for the Van Hoff factor. It's a correction factor. The same thing for Kf and Kb. They are physical constants that more or less hold for these solvents at low concentrations, but they're not real. Like if you start, so I think the example I saw, if you start getting above like 0.1 molar, these Kf and Kb values actually begin to change because there's enough ions in the solution now that they actually begin to affect the molecules on a much larger scale. So yeah, we leave it out because it's engineering. It's not really science. It's a nice approximation, but there's no theoretical basis for it. Because if you look at something like, I think it's MgCl2. It's 2.7, which we would expect to have 3 because there's 3 ions in this. So the reason why the 2.7 there is that if you look at water, so we have our Kb here at 1.86. If we did MgCl2 or NaCl or any of the others, in order to keep this constant, we just start varying the Van Hoff factors to make sure that the Kb was constant among all the solutions. So engineering is very much about wanting to get numbers. So it's very practical and it's very hands-on, but the thing about engineering is that it doesn't concern itself with a fundamental reason why something is happening. So with engineering, a good example of this is Beer's law. So Beer's law says that the amount of light absorbed is linear to the concentration. So if we look at the concentration of something and how much light it absorbs, Beer's law can prove that it's a straight line. And we can use probability arguments. So what a scientist would do is sit back and say, okay, what's fundamentally going on? And when they do it, they would get this linear formula. So C is the concentration, B is the path length, and A is a physical constant. And they would say it should be a straight line. And then they would plot the data and they would get the straight line. The engineer would not bother with that. What the engineer would do is they would plot the data and they'd say it looks straight, so I'm going to draw a straight line. I'm going to get y equals mx plus b. Now there's no proof, there's no reason to believe that this is a straight line, but for the engineer within the concentrations of questions it looks linear, and the only thing they really need is a number. So they create a formula which has no theoretical basis but allows them to get numbers that they need to perform a calculation. The worst of this, especially from my experience, are what are called the unitless numbers. So engineers need to make predictions, and so they have all these unitless numbers that they correlate to a whole bunch of measured data. And you'll get these really weird, like some number raised to like the 2.9863 power because it fits the graph. But there's no theoretical proof that this works, it just happens to fit the graph. So that's the big difference. Engineers do not concern themselves with why it happens. They need to be able to make a prediction. If they happen to have a theory, that's great, but they don't need it. Science wants an explanation. So you can put a straight line through anything, but in science you have to be able to prove why it should be a straight line. You just can't add it. Actually, no, really good example of this. And we'll talk about this when we get to the next test. The rate of reaction versus the concentration. There's what's called Michaelis-Mitten Kinetics that looks like this. And so the rate here is some constant times the concentration over 1 plus another constant times the concentration. And you can prove this. This is true. The thing is, an engineer wouldn't do this. The engineer would look at the data. Well, if the engineer is only looking from here to here, they'd say, oh, it's linear. Rate equals some constant times the concentration. If they were up here, they'd say, oh, the rate's constant. And if it was between here, they'd say, oh, it looks parabolic, so it looks like rate equals K concentration minus the concentration squared. There would be some formula. Now, you can take this rate law and prove that for low values of concentration, the rate looks linear, and for high values of concentration, it looks zero order. And then this formula accurately describes the bridging region. Yeah, so engineers are basically, they want a number. And because of this, it really limits them to the range over which they covered the data. Test 2 is rates of reaction. So rates of reaction is when we start getting really back into fundamental chemistry. Now, engineering does actually have some fundamental aspects of it. When it comes to reaction rate theory, actually engineering is much better at understanding reaction rates than a chemistry approach, which is why I teach it more from an engineering approach. But for the most part, like engineers just need a number, and so they don't care if there's a theory backing up what they're doing. And it's give and take. Engineers don't care about the theory because they don't need to care about the theory. They're there to produce a product. Scientists want to understand what's going on in the hopes that by understanding it, we can like come up with something new and better. But yeah, reaction kinetics are my favorite part of Chem 2. Because there's so much you can do with a simple thought experiment and make so many good predictions. Because the assumptions of reaction rate theory, transition state theory, they're all very simple assumptions and they have such power. So, covalent crystals, everything has to be connected. So, diamond is the ubiquitous example of this. If you look at a, I'm not even going to try to draw that. If you look at a covalent crystal, basically you're just going to have like a whole bunch, it's going to look like a big molecule. Molecular crystals, basically you have a whole bunch of molecular molecules that are just stacked on top of each other, but they're not actually bonded to one another. So I think the example I give in the notes is like crystalline oxygen, O2. When we have crystalline O2, it's just a crystal of O2 molecules. They're not bonded to each other. They're just stacked on top of each other to form the crystal. Whereas diamond is one super network of carbon atoms all bonded to each other. You're never going to be able to like pull like individual carbon atoms out like you could with an oxygen crystal where you could pull out individual oxygen molecules. Hello, Vera. exam 1, oddly, the phase diagrams are the ones where I see people making the most mistakes. And this is something I miss about the in-person. It's a cognitive cognitive blind spot in your understanding. So the PowerPoints for this section talk about the phases of matter, gas, solid, liquid, and plasma. But it begins to talk about how there's other phases within those phases. So within solids, you've got different crystals. You've got cubic, BCC, SEC, tetragonal. You've got a whole bunch of them. And so when students see a phase diagram, I will ask them, how do you know what the phase is? And they will say to me, it's written on the phase diagram. And so I will give a phase diagram and I will say, what's here? And they'll say solid. But the phase diagram says FCC, BCC, liquid, and gas. And I'll ask them, where do you see solid written anywhere on this phase diagram? And they look at me and they go, but it is a solid. I was like, you don't see solid written anywhere on here, so how do you know that it's solid? And that's when it begins to click that high school education, you're taught solid, liquid, gas. And so you don't actually read the phase diagram, you just start automatically assuming that's written in there. And the shame is, like, this is a lot of points on the exam because it's such a super easy question. But I've seen a lot of students say, oh, you start here, go here, go here. Well, it starts as a solid, goes to a liquid, then becomes a gas. It's like, well, no, it's not a solid, it's an SCC crystal. It told you specifically on the phase diagram what's on there. But other than that, really, this is a pretty straightforward plug and chug exam. The problems on those packets and the problems on the homework are actually substantially harder than anything you're going to see on the exam. So yeah, if you're doing the homeworks and you're getting packets, you're going to find the exam is very much akin to what's being done on the exam. The biggest complaint I get from students is the multiple choice questions. And it's not that they're unfair, it's just that there's no partial credit with those. It's 2 points and it's binary. But they're all knowledge based. And I tend to emphasize much more critical thinking on my exams. And I think that's more where the frustration comes from the multiple choice. An SEC is a crystal, but it's a specific type of solid. And that's the thing with the phase diagram is that if you say, well, it's solid, that's not really doing justice to this phase diagram. Because we're talking about, so you have SEC, BCC, liquid, and gas. And if you said, oh, well, it's a solid, solid, liquid, gas, you're not really reading the phase diagram. The point of the phase diagram is it tells you what the phase is, and the phase here is the FCC crystal, or the BCC crystal. And I did SEC and BCC because you know what those are, but I could definitely put something on here like tetrahedral, or no, what's it called? I'm forgetting what it's called. There's some weird crystal structures I can give you. But you would be more accurate to say SEC, BCC because those are the actual crystal phases. Van Hoff factors, typically we only apply to those because for organic compounds, the Van Hoff factor is generally assumed to be 1. That's not really right, but it's right enough. So again, an SEC crystal is a solid, but not all solids are FCC crystals. So to say it's a solid is like, you're right, but you're right in the sense that if I asked you what's 2 times 5 and you said, well, it's somewhere between 5 and 15, you're not wrong, but you would not say that's a meaningful answer. Yeah. So again, if I asked you what 2 times 5 was and you said, oh, it's between 5 and 15, it's like, you're not wrong, but you are wrong. Like the answer is 10. There's a much more precise answer there. So the phase diagram is an open-ended question. So again, just make sure you're actually reading the phase diagram. You're just not assuming what's on the phase diagram. For the multiple choice questions, they are engineered in such a way that you can get an answer even if you've done it wrong. It pros for certain mistakes, which gives me a feel for how you're lacking information. But yeah, I try not to ask questions, particularly with multiple choice. I try not to ask ones where like there's a lot of gray area for the debate. Again, I would argue this phase diagram is not really a gray area. It's like that's a really generic answer. You clearly weren't. You didn't need to look at the phase diagram to answer solid, but you did need to look at the phase diagram to say FCC, BCC. So yeah, just be accurate. It's a free response question. So I guess yeah, technically essay, but it's not like I don't want a paragraph. Like if you look at the packets, there's a discussions about phase diagrams. They're hard to write WebAssign questions for, but you're just basically saying based on what's going on in terms of what we're doing to the material, what phase you expect to see and what's happening. You too. Thanks for showing up. All right, any other questions out there? So determining the IMFs of a molecule, this is why I emphasize the functional group. So you could draw it, and some instructors do this. But it's a lot more helpful if you look at the functional groups. So when it comes to functional groups, there's 4 that you're responsible for. The alkyl, alkyl halides, so CCl, CI, CBr. an alkyl halide is just an alkyl group with one of the hydrogens swapped with a halide. So iodine, fluorine, bromine, chlorine. Your ketone and your alcohol. And so with each of these groups, we've got dispersion, dipole, 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 and H bonding. So you don't even need to draw the Lewis structure to figure out what's going on with the IMFs. You can just look at it and say, oh, this is an alpha group, so this is dispersion, 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 and that CH2 is going to be dispersion. The CO here is going to be dipole, dipole, and your OH is going to be H bonding. Now typically we report the strongest one, so in this case our alcohol is the strongest, so we're going to say this molecule interacts through hydrogen bonding. But this is the speed of using the functional groups. You don't need to draw out these Lewis structures because you know that each of these functional groups have these particular functionalities, and with those functionalities that'll tell you what the IMFs are. So in principle I could draw anything for you that contain these functional groups. So if I had CH2, Cl, CH2, CH3, we've got two alkyl, so it'll be dispersion, and then I've got an alkyl halide, and that's dipole, dipole. But yeah, I would say drawing the Lewis structure is overkill. You don't really need it. That's what the functional groups are for. And this is actually something we've been doing for about 2 years now. At least some instructors are starting to get on board with this idea. It's teaching you functional groups and not drawing the Lewis structure. Because the thing about the Lewis structure, there are rules for what's considered polar and nonpolar. It gets hard because when we teach you those rules for polar or nonpolar, we're typically only working with atoms that have molecules that have one central atom surrounded by periphery atoms. These are chains. And so what becomes polar and nonpolar in chains, there's different rules for that. So as a rule of thumb, we typically use the functional groups instead. And the thing is that we also kind of have to get you away from this idea that a molecule is polar or nonpolar. Polarity and nonpolarity are a spectrum. The only atoms that are truly nonpolar are actually just helium. Actually, even the lower noble gases have some degree of polarity to them. And the only truly polar molecules are column 1 metals, lithium, sodium, potassium, rubidium, bound with something like chlorine, bromine, or iodine. Those are the only true polar molecules. Everything else exists between the two. So hydrogen bonding here comes about from the fact that the OH group, even though it's covalent, acts ionic. Yeah, especially with huge molecules. And the thing is, like, it's also nice set up for organic. So organic chemistry, you learn, they stop using those formulas and they start going to things like this. And you can write out this formula. I think it's C6H5, CH, CH3, CHOH, CH, COOH, CH3. You can try and write it out this way, but it's the same line of reasoning. Like, these are all alkyl groups. So we know that these alkyl groups all do dispersion. There's your hydrogen bonding alcohol. This is a benzene ring. You would learn about like how this uses pi stacking. So this is technically dipole, dipole. And then you've got the H bonding from the carboxylic acid. But without ever having to draw the Lewis structure, you can rapidly identify all this information. So if an organic student saw this formula, they could quickly recreate this, and without even having to draw it, they could tell you what the polarity is of all those groups. Way more efficient. And it's the way chemists think about it. Divide it into a whole bunch of little problems. So the reason why we typically this is kind of okay. So your question is, why doesn't a functional group express more than one intermolecular force? The reason being is that it's so simple. These intermolecular forces just come about from charge separations. So we have two atoms, A and B. One is positive and one is negative. And the strength of this difference is the IMF that comes about. So if we have a really strong, we've got ionic, we've got H bonding, dipole, and then dispersion. So really it's just the electronegativity difference between two atoms. And the reason why a functional group can't have more than one intermolecular force is because really we're only looking at maybe 2 or 3 bonds and they're the exact same. So something like a CH3 group or a CH group, CH2 or CH, these are all just looking at carbon-hydrogen electronegativity differences. So there can only be one intermolecular force because there's really only one type of bond in here, a CH bond. For an alcohol, OH group, we've only got one bond, and that's the OH bond. And for something like a ketone, we've only got one bond, the carbon-oxygen bond. So the reason we can't have this spectrum is that we would need a variety of bonds in order to get the different strengths because we need a variety of charge differences between two atoms. In the case of functional groups, we've narrowed it down so there's really only one type of bond in that particular functional group. So it can only have one type of IMF. But this is why molecules end up having multiple IMFs, is because they do have different atoms bound to each other. So you have CH bonds, CO bonds, OH bonds, and that's why a molecule can have multiple IMFs. Hey, you're welcome. Again, with functional groups, what we try to do is we try to group it down to the smallest groups we can get, and then we just take them all together. It just doesn't get simpler than a functional group. I was about to give you a really bad analogy that I know you wouldn't understand. I was like, oh, it's like space groups. It's like, don't, no, just don't. All right, so not seeing anyone else. Got 0 concurrent viewers right now and only got a couple minutes left. So again, with any of these videos, please, these live streams are office hours. If you're not able to make them, feel free to send an email in advance. This is very much meant for basically if you need questions answered. Again, these aren't lectures, so if you want lectures, go to the course website. There's lots of videos on how to do these techniques. I will see y'all, hopefully see some of y'all tomorrow.